Welcome to lecture number 22 of PH 4105 Advanced Mathematical Physics. We are studying differential geometry, and in the previous lectures we have met a kind of entity which is of great importance: covariant tensors and covariant tensor fields. Let me just briefly remind you that a covariant tensor Tp at the point P of rank K, also known as a 0K tensor at P, is a multilinear map from the Cartesian product of TPM with itself K times to R. In other words, it's a map which takes in K tangent vectors tangent to the manifold M at the point P and returns a number in a linear fashion. Multilinear fashion, that means it's linear in each and every one of the arguments. We also extended this notion to get to the notion of a covariant tensor field T of rank K, also known as a 0K tensor field T on the manifold M. This was defined to be a map which assigns to each point P on M a 0K tensor Tp at M. And this definition immediately leads to an equivalent statement that a 0K tensor field T can also be seen as a map which takes K vector fields and maps them in a C-infinity multilinear fashion to a function M, where the function's value at the point P, this function T of x1, x2, xk at the point P, is nothing but the value of the tensor field T at the point P, namely Tp, acting on the tangent vectors at the point P which are obtained by taking the value of x1, x2, etc. respectively, each at the point P. Now, using these definitions, we had actually derived several results and also talked about different operations that you could do on covariant tensors. One important result that I'm going to quote now is that in particular, once you are given a coordinate patch u, phi with coordinate functions x1, x2 up to xn, a tensor field is completely determined within the domain U of the coordinate chart by the following n to the power k functions. T, I1, I2, Ik are all defined to be functions which you get when you apply the tensor field T on the arguments del del x I1 through del del x Ik. Of course, these are all the coordinate basis vector fields, so to speak. And once you have these functions, the tensor T can be written down in the following form: T I1 I2 Ik multiplied by dx I1, tensor product with dx I2, tensor product with dx I3, etc., all the way to tensor product with dx Ik. Now, this of course is defined within a single coordinate patch. If you move on to an adjacent coordinate patch, where the two domains U and U prime have an overlap region, you should be able to relate the components that you obtain using one coordinate system to the components that you obtain using another coordinate system. We had worked this out in the last lecture and shown that this actually leads to the standard, well-known transformation law for components, which a physicist often uses to define a tensor. So a tensor is really a rather straightforward thing. It's a multilinear map which maps vector fields to functions. But since we very often don't start with a fully differential geometric picture when we are dealing with physics, we are often constrained to define a tensor in a rather non-intuitive way as something which has a bunch of components which transform in a particular manner. But this transformation is obvious and immediate when we actually define a tensor field through differential geometry. Now, in today's lecture, what we are going to do is take a look at other kinds of tensors, namely the so-called contravariant tensors, which is an old term, and mixed tensors. Now, since we have already taken a look at the covariant or 0K tensor and 0K tensor field in some detail, and most of what we are going to do today mimics that very, very closely, I am going to go very fast. In fact, perhaps this particular lecture could have been omitted altogether because, frankly, you will see very, very similar results to the previous lectures. However, for the sake of completeness and also for the sake of keeping the logic intact, we have to talk about these things. I will go through this at a much faster pace and also with much less detail than in the previous lectures. I am hoping that that will not really be a deterrent. Of course, you can always find these things that I'm talking about in textbooks. So even if you find today's lecture to be too sketchy for your taste, you can always refer to the textbooks. The first new kind of object that we are going to deal with used to be called contravariant tensors. The modern notation for them is a tensor of type K0. Although many textbooks still refer to them as contravariant rank K tensors. A tensor of rank K0 at P is a multilinear map, but this time it's a multilinear map from K copies of Tp star M, the set of all covectors at the point P, as opposed to Tpn, the set of all tangent vectors at the point P. Of course, this was just a domain of the map. The range is R. And in a sense, this is very, very similar to 0K tensors that we had met before. The only difference being that here the arguments are covectors rather than vectors. Now, when we have a coordinate system in play, a coordinate system u, phi, with u being the domain of the chart and phi being the map, with coordinate functions x1, x2, xn making up the map phi, we know that Tpm, the set of all tangent vectors at the point P of the manifold, has a standard basis in terms of these coordinate functions. These are given by del x1p, del x2p up to del xn at P, which are the tangent vectors at P to the distinct coordinate curves. Now the dual to this set of vectors gives us a basis for Tp star M. These are the coordinate differentials dx1, dx2 up to dxn at P. And the important point is, these dxiPs form a basis of Tp star M, and as a result, all covectors can be written down as a linear combination of dxiPs. So you can always write a covector alpha as alpha I dxip, if alpha is a covector at the point P. And alpha I, these numbers, are nothing but the values which you get when alpha, the covector, acts on the coordinate basis vector del xi at the point P. So we get this result that alpha is alpha del xi at the point P, the component alpha I, times dxip, of course summed over all I. Now using this, we can write the result of Tp, the K0 tensor acting at P, given arguments alpha 1 to alpha k. Each of these are covectors at the point P in the following fashion. You can write each one of the arguments alpha 1 through alpha k using this expression. So alpha 1 becomes alpha 1 acting on del x I1p dx I1p, summed over I1 of course, and so on. Similarly, alpha k becomes alpha k acting on del x ik at p times dx ikp, and so on. Now, these objects here, coefficients of the dxi's, are just numbers. And since Tp, the K0 tensor, is a multilinear map, you can pull out all of these numbers, and this becomes the same as Tp acting on dxi1p through dxikp times these numbers. Now, we define the action of a vector v at P on a covector alpha p simply by saying that this returns a number which is alpha p times Vp. Alpha p acting on Vp. And therefore, we can write each one of these numbers here as del x I1 acting on alpha 1, del x I2 acting on alpha 2, and so on, all the way to del x ik acting on alpha k. And the object here, which is just a number, can be written down as Tp I1, I2, Ik. These are just Tp acting on the coordinate differential basis vectors of TP star M. Now, finally, according to the definition of tensor product of vectors, this simply becomes del xi1p tensor product with del xi2p del xikp acting on alpha 1 alpha through alpha k, of course, with an overall weighting factor of tp i1 i2 ik. Now, since this works for all alpha 1 alpha 2 alpha k which are cotangent vectors at p, we immediately end up with tp being equal to tp i1 ik del xi1p tensor product with del xi2p tensor product with del xi3p up to del xikp. So these tensor products of all the del xips, all possible tensor products of k of them, gives us a basis of the set of all k0 tensors, and the coefficients tp i1 i2 ik, this bunch of n to the k numbers, gives us the components of tp according to this coordinate. Let me just remind you that this is again very similar to what we saw with 0k tensors. There, a tensor tp was again given by tp i1 through ik, but there we wrote the indices as suffixes, and here we are writing them as superfixes, primarily so that we can distinguish between these two kinds of objects. But there, the components were nothing but tp acting on del xi1p, del xi2p up to del xikp. Here, tp with the superfixes i1, i2, ik are nothing but tp acting on dxi1p through dxikp. Another way of writing the action of tp on alpha 1 through alpha k is simply writing it in terms of the components of both the tensor tp and the components of alpha 1 through alpha k. And there you simply get tp i1 i through ik times alpha 1's i1th component, alpha 2's i2th component, all the way up to alpha k's ik component. All of them, of course, summed up over i1, i3, ik, and so on. These alpha 1, i1, alpha 2, i2 are nothing but these coefficients, alpha 1 acting on del xi1, alpha 2 acting on del xi2p, and so on. Now, a while ago I just mentioned that these tensor products actually form a basis of the set of all k0 tensors at the point P. Now, that of course hinted at the fact that if you take all the k0 tensors at the point P belonging to M, this set, also known as Tp with a superfix k0 on M, that's the shorthand, is a vector space. Now, of course, to be a vector space, you have to define how to add two elements of this, how to multiply them by numbers, and that's sort of very straightforward. You define ATP plus BSP for all A and B real numbers and all members of TPK0M, that is, all K0 tensors, TP and SP. In the following manner, you define this as a multilinear function which acts on alpha 1 through alpha k, just to give you the number A acting on TP alpha 1 through alpha k plus B acting on SP alpha 1 through alpha k. The proof that this is really a multilinear function from the set TP star M cross TP star M all the way up to k such factors to R is actually a pretty straightforward thing to prove. And I will leave that as an exercise for you. Let us come now to the final kind of tensors, the so-called mixed tensors, a tensor of type k, L. Now, rather obviously, it maps k covectors and L vectors at the point P multilinearly to a real number. So, it's a map whose domain is the Cartesian product of k TP star M's and L TPM's, and the range is R, the set of all real numbers. What is important? It is multilinear in all its arguments. Now, you have a very natural way of defining the sum and product by a scalar or a real number of KL tensors at the point P, very similar to the definition that we gave just a while ago. And using that, the set of all such tensors, which we will call TP with a superfix KL at M, is going to be a vector space. Now, Another important operation that we need to talk about is the tensor product of a KL tensor and a K prime L prime tensor. This is going to give me a K plus K prime L plus L prime tensor at the point P using in the rather obvious manner in which you have a map here which takes K plus K prime covectors and L plus L prime vectors and maps them to a number. The first K of these K plus K prime covectors go to the first KL tensor. The first L of the vectors also go there as arguments. And the final K prime covectors and L prime vectors are given to the K prime L prime tensor. Again, using a coordinate chart, it is very easy to form a basis for this space. And the basis here, as you would expect, is actually given by K copies of del del x I1, del del x I2s being tensor producted and L copies of dx's being tensor producted. All of them together. And it's rather easy again to see that this space has a dimension which is given by n raised to the power k plus l. After all, if this is a basis, each one of these indices I1, I2, Ik, J1, J2, Jl, k plus l indices and all, can take n independent values. So overall there are n to the power k plus l distinct such basis vectors, and they span the whole set, which immediately tells you that this is the dimension. Now that we have defined various kinds of tensors at a point, let us talk about tensor fields. And let us begin with contravariant tensor fields, or to be more modern in our language, a tensor field of rank K0. Now, in order to define this formally, we need to first introduce the notion of a tensor bundle, Tk0m. This is the union over all points P of the manifold of the vector spaces which you get, the n to the k dimensional K0 vector spaces which are made up by all the K0 tensors at the point P. So this is basically a collection of all tensors at all points of the manifold. Now a tensor field of rank K0 is a map from M to this particular tensor bundle, the K0 tensor bundle Tk0m. What does it do? It assigns to every point P belonging to M a member of Tpk0m, that is a K0 tensor at the point P. Note that this is exactly similar to the way in which we defined 0k tensor fields. The only difference here, of course, is the rank or kind of tensor that is being assigned at every point. Now, in terms of coordinates, a K0 tensor field T can be written in this form. T dxi dot dxk. This, when you feed the tensor field T a bunch of covector fields, or rather a bunch of one forms, what you get is a function. Now, I'm not going to go into the details of this because this is exactly similar to what we did for 0k tensor fields in the previous lecture. This is a function, or rather it's a bunch of functions, one for each set of indices I1 to Ik, into the k functions to be precise, and they, multiplying this tensor product of del del xi1, del del xi2 up to del del xik, gives us a representation of the tensor T. This representation, of course, is tied to this particular coordinate system. If you change your coordinate system, the x's will change, so will the basis vector fields del del x's, and of course, so will these one forms here, and overall the coefficients are going to change. Now, we call a K0 tensor field smooth if for all one forms, alpha 1, alpha 2, alpha k, not just covectors but smooth covector fields, T alpha 1 to alpha k is a smooth function. Now this happens if and only if these n to the k functions, which we write as t upper I1 to ik, which is just this, are smooth. Each and every one of them. Now, what about mixed tensor fields? A tensor field of type k, L assigns to every point P of M or some region U of M. The tensor field may not be defined over the entire manifold, but only over a region U. A tensor of type KL at the point P. So, the similarity should be clear. A vector field assigns to every point P on a manifold or a region of that manifold a vector tied to that point, a tangent vector at that point. A covector field defines at every point P a covector at that point. A 0k tensor field assigns to every point a 0k tensor tied to that point, a k0 tensor field, or a contravariant tensor field of rank k assigns to every point a k0 tensor at that point, and finally, as we have just stated, a mixed tensor field assigns to every point P a mixed tensor at that point. A very special case of this is the case where K and L are both 0. A tensor field of type 0, 0 essentially assigns a 0, 0 tensor, just a number at every point P of the manifold, so it's nothing but a function on M. So a function is a special case of a tensor as well. A tensor of contravariant and covariant ranks 0 each. Now, we define a KL tensor field as smooth if for any x1 through xl, which are smooth vector fields, and alpha 1 through alpha k's, which are smooth covector fields or one forms, the function t x1 through xl alpha 1 through alpha k, which is defined, of course, by its value at the point P being given by Tp acting on x1p, x2p, xlp, alpha 1p, alpha 2p, alpha kp, etc. This function is a C-infinity function. And it should not be very difficult to guess that you can define linear combinations, products by functions in this case as opposed to by numbers, and tensor products or mixed tensors. All of them can be defined point-wise. So at every point, a mixed tensor field gives you a mixed tensor. And because we know how to linearly combine mixed tensors, multiply mixed tensors by numbers, and form direct products of mixed tensors, we essentially know how to form the corresponding results for tensor fields. Notice that when you multiply a tensor field T, some KL tensor field, by F, a function, a smooth function, the result is a new KL tensor field whose value at the point P is given by the value of the function at P times Tp. Similarly, when you form a tensor product of a KL tensor and a K prime L prime tensor, you do it point-wise. At every point P, the tensor product of the two mixed tensor fields is given by the tensor product of T at that point and S at that point. Now, as we have already seen, the set of all tensors, say KL tensors at a point P, form a linear vector space of dimension into the K plus L. And from these conditions, especially the first two, it would seem like the set of all tensor fields also form a vector space. However, you have to be a bit careful because here the linear combination is being done by functions and not numbers, and functions do not form a field in the algebraic sense of the word. What they do is form a ring. So the set of all smooth functions C infinity M is a ring because there are elements in it which are not zero but which you cannot divide by. Functions which vanish at one or more points in the domain cannot be divided by despite the fact that they are not identically zero functions, which is what makes C infinity M a ring rather than a field. And so what you get when you take the set of all smooth KL tensor fields and use those definitions above to form linear combinations is not really a vector field because that requires the scalars to form an algebraic field. is what is called a module. So the set TKLM of all smooth KL tensor fields is a module over the ring C infinity M. Of course, this set is also a linear vector space over R, but restricting the multipliers only to numbers sort of detracts from the power of tensor fields. So we ignore the vector space structure and focus more on the module structure of TKLM. Note that whatever we have said here so far is valid for all non-negative K and L. So the statement that TKLM forms a module over the ring C infinity M is actually also valid for TK0M, that is, the set of all smooth K0 tensor fields, or for T0KM, that is, the set of all smooth 0K tensor fields as well. We are next going to talk about component functions of a tensor and also about how these component functions transform when you change your coordinates. Now, these statements could also have been made separately for 0K fields and K0 fields, but I'm going to only state this for KL fields, and this is going to cover all the cases. In fact, the case for 0K fields has already been covered in the previous lecture. So, what I'm going to say now should seem pretty familiar. Now, in such a situation, you have to start with a chart u, phi, which has coordinate functions x1 through xn. And we know that every vector field can be expanded in terms of del xi's, the coordinate basis vector fields, in the form capital Xi del Xi. And every one form omega can be written down in the form of omega j dxj. And these capital Xi's can be found out simply by applying dxi's, the coordinate differential one forms, on the vector field x. And similarly, the omega j can be figured out by applying del xj, the coordinate basis vector field, the jth coordinate basis vector field, on omega. Now, a tensor T of rank k, L is of course a map which takes k vector fields and L covector fields or one forms and gives you a function as a result. Now here what we can do is write each of these arguments in terms of the corresponding basis vector or covector fields. So x1 can be written down as x1 i1 del xi1, x2 i2 del xi2, up to xk ik del xik. Then note that you have to write i1, i2, etc. different indices for each one of them just to ensure that the dummy indices are regarded as separate indices and not mixed up together. Now these are only for the vector fields. You have to do the same also for the covector fields. Omega 1 is omega 1 j1 dxj1. Omega 2 is omega 2 j2 dxj2. And omega L, the final one, is omega ljl dxjl. Now, the important point here is that each of these quantities here, the x1 i1, x2 i2, omega ljl, they are all functions. And a tensor field T is a C infinity multilinear object. So all of these functions can be pulled out of the arguments and you end up with this expression. T acting on this bunch of specific vector fields, the coordinate basis vector fields and coordinate differential vector fields. And these are multiplying functions which you multiply this result by. So it's easy to see that this bunch of functions, this is not a single function, of course. You get one such function for each value of i1, i2, ik, j1, j2, jl. So these are really n to the k plus l functions. They completely specify what the tensor is going to do to every set of arguments. Essentially, they tell you what the tensor is. Now, these functions, as we said, completely specify what the tensor is by telling you what the tensor does. It gives you this combination of sums of products of functions as a result of its action on x1, x2, xk, omega 1, omega 2 up to omega n. Now there's a slightly different way of writing this, which is the following. You can take this function, which is this t I1, I2, ik, j1, j2, jl, multiplied by x1, I1, which is really dx I1, x1, then dx I2 acting on x2 gives you x2, I2, and so on. And omega 1, j1 is nothing but the coordinate differential vector field del del x j1 acting on omega 1, all the way up to del del x jl acting on omega l. Note that we have deliberately placed the indices in a particular manner. All the so-called covariant indices have gone below and all the contravariant indices have gone up, and that actually is perfectly consistent with our rule that summation will be done only over an upstairs, downstairs index pair. Now, notice that this bunch of functions, the components of the various vector fields and the covector fields that are multiplied together, can also be seen as the result of this tensor product dxi1 all the way to dxik, then del del x j1 all the way to del del x jl, getting to act upon this bunch of arguments. Note that whenever a tensor product is fed a series of arguments, the arguments are given to the individual elements in sequence. So this is really dxi1 acting on capital X1. dxi2, the next element of the tensor product, will act on capital X2 and so on, which is exactly what you have here. But notice the t acting on this set of arguments is exactly equal to this whole thing acting upon this bunch of arguments, same bunch. And this works for all smooth arguments that you can give. And so you can say that the tensor t is the same as this t I1, I2, ik, j1, j2, jl. These are the component functions. You have to multiply them by a basis. dxi1 tensor product with dxi2 all the way up to tensor product with dxik, then tensor product further with del del x j1, del del x j2 up to del del x jl. This is a complete characterization of a tensor provided you are using a coordinate system. Now, an immediate question that arises whenever you talk about a coordinate system is, what happens if you use another one, a different coordinate system? Of course, that means that we are talking about two charts, u comma phi and u prime comma phi prime, with coordinate functions x1 through xn for u phi and x prime 1 through x prime n for u prime phi prime, and there is an overlap region. U intersection u prime is non-empty. In that region, you can use both set of coordinates, the unprimed ones and the primed ones, and now it is a legitimate question to ask, how do the component functions change if you were to change your coordinates? And the answer follows directly from what we have just said. This t prime a1 ak up to b1 bl, that these are the components of the new coordinate frame, is simply the tensor t acting on del del x prime a1 all the way up to del del x prime ak, then dx prime b1 all the way up to dx prime bl. And that is nothing but this expression, which is the tensor t as we have just seen, but written in terms of the old or unprimed coordinate system, getting to act upon this series of arguments. Now, once again, what does the tensor product do when it's fed a series of arguments? It just feeds the individual terms, each of the arguments in turn. So, this expression is the same as dxi1 getting to eat up del x prime a1, dxi2 getting del del x prime a2 as an argument, all the way up to dxik getting del del x prime ak as an argument. But then you have dx prime b1. This argument is given to del del x j1. dx prime bl is given to del del x jl, and all the other terms in between are also there. Now notice that this thing is exactly what we denote by del x I1 del x prime A1. I'm saying denote by to make you aware that this is really not a partial derivative in the standard sense of the word. But once again, since whenever we think of x's as functions of x primes and vice versa, we are really talking in terms of transition functions. Thinking of them as partial derivatives will not really harm your case at all. But putting them all together, you get the transformation rule. The new components of t in the new coordinate system are basically linear combinations of the old components of t, but with factors which are different kinds for the lower indices and for the upper indices. This essentially is the phases definition of a mixed tensor. Essentially a bunch of components which transform in a particular manner. Said earlier in the case of covariant tensors, even for mixed tensors, this transformation rule is an immediate consequence of the basic definition of a KL tensor as a multilinear map. Now there are many more results I could talk about, but they are also similar to the corresponding results that we had derived earlier for 0K tensors and tensor fields, that they don't really bear repetition any longer. We will move on next to a special kind of 0K tensor field, the differential forms, and see how extremely useful a very specially restricted form of tensor field can be. But that is for the next lecture. Goodbye for now.